Welcome to Sleepy Science Hub. I'm so glad you found your way here tonight, to this peaceful corner of the cosmos where we explore the universe's gentlest mysteries together. As you settle into your most comfortable position, wherever you might be in the world right now, take a moment to let me know in the comments where you are and what time it is as you listen. There's something wonderfully comforting about knowing we're sharing this quiet moment of cosmic exploration together, connected across our small planet, while we journey through the vastness of space in our imagination. Tonight, we're going to embark on a gentle voyage through the cosmos to discover some of the universe's most peaceful wanderers, rogue planets. These are worlds that have broken free from the gravitational embrace of their home stars and now drift serenely through interstellar space, carrying with them stories of cosmic journeys that span millions of years. Don't worry about complex astrophysics or dramatic cosmic catastrophes. We're approaching these celestial nomads as peaceful observers, following their quiet journeys through the infinite dark with the same gentle curiosity we might bring to watching clouds drift across an evening sky. Now, get comfortable. Adjust your pillows, pull your blankets close, and let your breathing settle into its natural, peaceful rhythm. Take a slow, deep breath. Feel your body releasing the tensions of the day, and let's begin this tranquil journey into the cosmic wilderness where worlds wander free among the stars. As you lie there in comfort, your breathing gradually slowing and deepening like the gentle rhythm of cosmic tides that flow between distant stars. Imagine yourself floating peacefully in the vast darkness of interstellar space. Here, in the quiet emptiness between star systems, you find yourself surrounded not by the harsh vacuum that science fiction might portray, but by a serene cosmic ocean filled with invisible currents of dust, gas, and magnetic fields that connect one corner of the galaxy to another in an intricate web of gentle influence and gravitational whispers. In this peaceful cosmic wilderness, far from the warm light of any star, you begin to sense that you are not alone. Drifting through this darkness with you are some of the universe's most remarkable travelers, worlds that have left their birth systems behind and now journey through space as cosmic wanderers, carrying with them the memory of distant suns and the promise of future encounters yet to come. These are the rogue planets, and they represent one of the most beautiful expressions of cosmic freedom and solitude in the entire universe. The story of rogue planets begins with understanding that our cosmos is far more dynamic and fluid than it might appear from our earthbound perspective. While we think of planetary systems as stable, eternal arrangements where worlds orbit their stars in perfect harmony for billions of years, the reality is both more complex and more beautiful. Star systems are actually dynamic environments where gravitational forces constantly interact, creating subtle dances that can, over vast periods of time, result in worlds breaking free from their stellar families to begin new chapters as independent cosmic wanderers. Picture a rogue planet as it appears in the darkness of interstellar space, a world perhaps similar in size to Earth, or maybe as massive as Jupiter, moving silently through the cosmic void at speeds of tens of kilometers per second. Yet despite this tremendous velocity, the planet appears to hang motionless in space. So vast are the distances between stars that even at these cosmic speeds, its journey from one stellar neighborhood to another spans millions of years. This is movement on a scale so grand that it transcends human comprehension, transforming speed into a form of cosmic meditation where change happens so slowly it becomes a kind of eternal present. As your consciousness settles into harmony with these vast scales of space and time, your breathing becoming as patient and measured as the orbital periods of distant worlds, you begin to appreciate that rogue planets represent a profound form of cosmic independence. Free from the gravitational constraints that bind most worlds to their parent stars, these wandering planets follow trajectories determined only by the gentle gravitational influences of the galaxy itself. They are cosmic nomads in the truest sense, carrying their own internal heat and atmosphere through the interstellar medium like self-contained worlds that have learned to find sustenance and stability within themselves. The number of rogue planets in our galaxy is truly staggering. Conservative estimates suggest there may be billions of these wandering worlds drifting through the Milky Way, possibly outnumbering the planets that remain bound to stars. This means that as you rest peacefully in your bed, countless rogue planets are silently journeying through space above your head, invisible and undetected, each one carrying its own unique story of cosmic adventure and solitary exploration. These wandering worlds come in all sizes and compositions, from rocky planets similar to Earth and Mars to massive gas giants that dwarf even Jupiter in their scale and majesty. Some rogue planets may have formed around stars, just like the planets in our solar system, only to be ejected later through gravitational interactions with other planets or passing stars. Others may have formed in the cold darkness of interstellar space itself, condensing from clouds of gas and dust without ever experiencing the warmth of a parent star. Each formation pathway creates rogue planets with different characteristics, atmospheres, and internal structures, adding to the beautiful diversity of these cosmic wanderers. The ejection process that creates most rogue planets is surprisingly gentle when viewed on cosmic timescales. Rather than violent explosions or catastrophic collisions, the creation of a rogue planet typically involves a slow gravitational dance that unfolds over hundreds of thousands or millions of years. A planet's orbit gradually becomes more and more eccentric as it interacts with the gravitational fields of other planets, neighboring stars, or even the central black hole of the galaxy, until eventually its orbit becomes so elongated that it carries the planet beyond the gravitational reach of its parent star. During this gradual ejection process, the planet doesn't experience any sudden trauma or dramatic transformation. Instead, it slowly transitions from being a world defined by its relationship to a star to becoming a self-sufficient cosmic entity that carries its own environment through space. If the planet has an atmosphere, that atmosphere remains largely intact during ejection. If it has moons, those moons typically continue to orbit their planet even as it travels through interstellar space. The planet essentially becomes a miniature planetary system unto itself, complete with all the gravitational relationships and atmospheric dynamics that characterized its earlier existence. The temperature environment that rogue planets experience presents one of the most fascinating aspects of their existence. Without the warming radiation of a nearby star, rogue planets exist in temperatures that hover just a few degrees above absolute zero, the coldest possible temperature in the universe. Yet this doesn't mean these worlds are completely frozen or lifeless. Many rogue planets retain significant internal heat from their formation process, and this geothermal energy can persist for billions of years, creating the possibility for subsurface oceans, atmospheric dynamics, and even potentially habitable environments that exist independent of any external star. The magnetic fields that many rogue planets possess provide another layer of protection and environmental complexity. A planet's magnetic field, generated by the motion of molten metal in its core, creates an invisible shield that deflects harmful cosmic radiation and helps retain atmospheric gases that might otherwise be stripped away by the interstellar medium. This magnetic protection means that rogue planets can maintain complex atmospheric systems even in the harsh environment of interstellar space, creating weather patterns, chemical cycles, and dynamic systems that continue to evolve throughout their cosmic journeys. The surfaces of rocky rogue planets present landscapes of extraordinary beauty and serenity. Without the erosive effects of stellar radiation or the complex weather patterns driven by solar heating, these worlds may preserve geological features for billions of years, creating terrain that tells the story of planetary formation and early evolution in remarkable detail. Ancient impact craters, volcanic formations, and tectonic structures remain pristine in the gentle environment of interstellar space, making rogue planets natural museums of planetary geology and cosmic history. For gas giant rogue planets, the lack of stellar heating creates atmospheric dynamics driven entirely by internal heat sources. The great storm systems and cloud patterns that characterize these worlds operate according to internal energy cycles that can persist for geological ages, creating atmospheric phenomena of incredible complexity and beauty that unfold in the darkness of space without any external observer. These atmospheric systems represent some of the most purely self-contained weather patterns in the universe, driven by forces that originate entirely within the planet itself. The detection of rogue planets presents extraordinary challenges that have pushed astronomical techniques to their limits. Since these worlds emit no light of their own and reflect no starlight, they are essentially invisible to traditional telescopes. Instead, astronomers must rely on their gravitational effects or the faint heat signatures they emit to reveal their presence. This has led to the development of increasingly sophisticated detection methods that can identify the subtle gravitational lensing effects that occur when a rogue planet passes between Earth and a distant star, briefly magnifying the star's light in a characteristic pattern that reveals the presence of the intervening world. The infrared signatures of rogue planets provide another window into understanding these cosmic wanderers. Even in the cold of interstellar space, planets continue to emit thermal radiation from their internal heat sources, creating faint infrared glows that can be detected by sensitive space-based telescopes. These thermal signatures not only confirm the presence of rogue planets, but also provide information about their size, composition, and internal temperature, allowing astronomers to begin characterizing these worlds despite their vast distances and extreme faintness. The gravitational microlensing events that reveal rogue planets are among the most subtle phenomena that astronomers have learned to detect and interpret. When a rogue planet passes directly between Earth and a background star, its gravitational field acts like a natural lens, bending and focusing the star's light in ways that create a characteristic brightening pattern lasting anywhere from hours to days. The precise shape and duration of this brightening reveals information about the mass and distance of the intervening planet, allowing astronomers to study worlds that are otherwise completely inaccessible to direct observation. The space-based surveys designed to discover rogue planets have revealed that these cosmic wanderers are far more common than anyone initially expected. Projects like the Kepler Space Telescope and the ongoing TESS mission have identified numerous microlensing events consistent with the presence of free-floating planets, while infrared surveys have directly detected the heat signatures of some of the nearest rogue worlds. These discoveries suggest that planetary ejection is a common process in the universe, and that the space between stars may be filled with a population of wandering worlds that rivals or exceeds the number of planets orbiting stars. The diversity of rogue planet types continues to surprise astronomers as detection techniques improve and more examples are discovered. Some rogue planets appear to be super-Earths, worlds larger than our planet but smaller than Neptune, that may have formed in the outer regions of star systems before being ejected. Others are massive gas giants that dwarf Jupiter and may have formed through direct gravitational collapse in interstellar space. Still others appear to be small, rocky worlds similar to Mars or Mercury that were ejected from the inner regions of their birth systems through complex gravitational interactions. As you continue to drift peacefully through this cosmic landscape in your imagination, your breathing now completely synchronized with the patient rhythms of interstellar space. You can begin to appreciate the profound tranquility that characterizes the existence of rogue planets. These worlds embody a form of cosmic solitude that is both complete and serene, traveling through space with an independence and self-sufficiency that represents one of the universe's most beautiful expressions of autonomous existence. They remind us that even in the vast emptiness of space, worlds can find ways to persist, evolve, and even potentially nurture life through resources and processes that originate entirely within themselves. The ongoing research into rogue planets continues to reveal new aspects of their nature and behavior. From the atmospheric dynamics that persist in the absence of stellar heating to the magnetic field interactions that occur when these worlds encounter the interstellar medium. Each new discovery adds to our understanding of how planets can exist and evolve in environments far removed from the stars that gave them birth, expanding our conception of what constitutes a habitable or potentially life-bearing world in the universe. As you settle deeper into peaceful contemplation, your breathing now flowing like the gentle gravitational currents that shape planetary orbits across cosmic time. Let your awareness turn to the remarkable process by which worlds break free from their stellar families to begin their solitary journeys through space. This transformation from bound planet to cosmic wanderer unfolds not through violent catastrophe, but through an elegant gravitational ballet that spans millions of years, demonstrating the universe's preference for gradual change over sudden disruption, even in events that fundamentally alter the destiny of entire worlds. Picture yourself floating above a young planetary system, perhaps 5 billion years ago, watching as multiple worlds orbit their star in what appears to be perfect harmony. The system looks stable and eternal from your cosmic vantage point, with planets following elliptical paths that seem as reliable as clockwork. Yet beneath this apparent stability, subtle gravitational forces are constantly at work, creating tiny perturbations and orbital adjustments that accumulate over vast periods of time like interest in a cosmic savings account, gradually building toward transformations that will reshape the entire system. The process begins with something as gentle as the gravitational influence of a distant passing star, an event so remote and subtle that it might take thousands of years for its effects to become apparent. This stellar visitor doesn't crash through the system or cause any dramatic disruptions. Instead, it simply passes by at a distance of several light years, its gravitational field creating barely perceptible changes in the orbits of the system's outermost planets. These changes are so small that they would be undetectable to any observer, yet they plant the seeds of a transformation that will unfold over geological timescales. As your consciousness settles into harmony with these vast temporal rhythms, your breathing becoming as patient and measured as the orbital periods that govern planetary motion, you begin to understand how gravitational interactions work like gentle sculptors, gradually reshaping planetary orbits through countless tiny adjustments. A planet's orbit becomes slightly more elliptical with each pass around its star, its path slowly stretching from a near-perfect circle into an increasingly elongated ellipse that carries it farther from its parent star with each successive orbit. The mathematical beauty of orbital mechanics reveals itself in these slow transformations, where small changes in velocity or position compound over time according to precise physical laws that govern motion throughout the universe. When a planet's orbital velocity decreases by just a few meters per second, a change so small it would be imperceptible to anyone standing on the planet's surface. That tiny adjustment begins a process that can eventually carry the world beyond the gravitational reach of its star. The universe operates on principles of such exquisite sensitivity that the smallest influences can have cosmic consequences when given sufficient time to develop. The three-body problem in celestial mechanics describes how the presence of multiple gravitational sources creates orbital instabilities that can lead to planetary ejection. When a planet orbits a star in the presence of other planets, the combined gravitational influences create a complex dynamical environment where perfectly stable orbits become impossible to maintain over infinite time. This doesn't mean that planetary systems are inherently unstable, but rather that they exist in a state of dynamic equilibrium where small perturbations can gradually amplify into larger changes that reshape the entire system's architecture. The resonance effects that occur when planetary orbital periods relate to each other through simple mathematical ratios create some of the most beautiful and powerful mechanisms for orbital evolution. When two planets orbit their star in periods that relate as simple fractions, 2-to-1, 3-to-2, or 5-to-3, their regular gravitational interactions can pump energy into their orbital motion in ways that gradually increase the eccentricity of their paths. These resonance relationships act like cosmic pendulums, steadily transferring energy between planetary orbits until one world gains enough energy to escape the system entirely. The correlative mechanism represents another elegant pathway for planetary ejection, named after the scientists who first described how the gravitational influence of distant companions can cause interorbital systems to undergo dramatic oscillations. In this process, a distant star or massive planet causes the orbit of a closer world to alternate between nearly circular and highly eccentric configurations over timescales of millions of years. During the highly eccentric phases, the planet ventures so far from its star that tidal forces or additional gravitational perturbations can provide the final push needed to break free from the system entirely. The role of stellar evolution in planetary ejection adds another layer of complexity to these gravitational stories. As stars age and change, their gravitational influence on surrounding planets can shift in ways that destabilize previously stable orbital configurations. When a star exhausts its nuclear fuel and begins to expand into a red giant, the changing mass distribution and increased stellar wind can alter planetary orbits enough to trigger ejection events. Similarly, when massive stars explode as supernovae, the sudden loss of stellar mass can unbind entire planetary systems, sending all their worlds flying into interstellar space as a cosmic diaspora. The formation of binary and multiple star systems creates gravitational environments that are particularly conducive to planetary ejection. When two or more stars orbit each other, their combined gravitational field creates regions of stability and instability that shift and evolve as the stellar orbits themselves change over time. Planets that form in apparently stable regions can find themselves in dynamically unstable environments as the stellar system evolves, leading to ejection events that occur millions or billions of years after the original planetary formation. The migration of giant planets through their birth systems represents one of the most common pathways for creating rogue worlds. Computer simulations of planetary system evolution show that massive planets frequently spiral inward or outward from their formation locations due to interactions with the protoplanetary disk or gravitational scattering events with other planets. During these migration episodes, smaller worlds can be scattered into highly eccentric orbits that eventually carry them beyond the gravitational reach of their parent stars. The concept of planetary scattering reveals how gravitational interactions can transform orderly planetary systems into cosmic billiard games where worlds exchange orbital energy through close encounters that unfold over thousands of orbital periods. When two planets approach each other closely enough for their gravitational fields to interact strongly, one planet typically gains orbital energy while the other loses it. The planet that gains energy moves to a higher, more eccentric orbit, while the planet that loses energy may spiral inward toward its star, or, if it loses enough energy, be ejected from the system entirely. The timescales involved in planetary ejection processes span ranges that challenge human comprehension, from relatively rapid events that occur over millions of years to gradual transformations that require billions of years to complete. These vast temporal scales mean that planetary ejection represents one of the most patient processes in the universe, unfolding with a deliberation that makes mountain building and continental drift seem rapid by comparison. The universe demonstrates through these processes that the most profound transformations often occur through steady persistence rather than sudden dramatic change. The statistical studies of planetary system architecture reveal that ejection events are far more common than early astronomers suspected. Observations of nearby star systems show that many display evidence of past dynamical instabilities, with planetary orbits that bear the signatures of gravitational scattering events and missing planets that were likely ejected during the system's early evolution. These studies suggest that most planetary systems undergo at least some dynamical evolution that results in the ejection of one or more worlds, making rogue planet formation a natural and expected outcome of planetary system development. The computer simulations that model planetary ejection processes have revealed the intricate beauty of gravitational dynamics operating over cosmic timescales. These simulations show planetary orbits evolving like slow-motion dances, with worlds gradually spiraling outward or inward in response to gravitational influences that operate with mathematical precision. Watching these simulations unfold is like observing a cosmic ballet performed over millions of years, where each gravitational interaction contributes to an overall choreography that ultimately determines which worlds remain bound to their stars and which break free to wander the galaxy. The energy requirements for planetary ejection reveal that these processes are remarkably efficient at converting small gravitational perturbations into the kinetic energy needed to unbind worlds from their parent stars. The escape velocity from a typical planetary system, the speed needed for a planet to break free permanently, ranges from tens to hundreds of kilometers per second, depending on the mass of the central star and the planet's initial orbital distance. While these velocities seem enormous by terrestrial standards, they represent only small fractions of the orbital velocities that planets already possess, meaning that relatively modest energy transfers can initiate ejection processes. The conservation laws that govern orbital mechanics ensure that planetary ejection events always involve trade-offs, where energy and angular momentum are exchanged between different components of the system. When one planet gains enough energy to escape, other planets typically move to lower energy orbits that bring them closer to their star. This creates a natural sorting mechanism where planetary systems gradually separate into tightly bound inner worlds and unbound outer worlds that escape to become rogues. The observational evidence for ongoing planetary ejection processes comes from studies of young star systems, where astronomers can detect the gravitational signatures of worlds in highly eccentric orbits that appear to be in the process of escaping their parent stars. These observations provide direct confirmation that planetary ejection is not just a theoretical possibility, but an active process occurring in star systems throughout the galaxy. Some of these escaping worlds may be caught in the act of breaking free, allowing astronomers to study the ejection process as it unfolds in real time across cosmic timescales. The diversity of ejection mechanisms means that rogue planets can originate from virtually any type of planetary system and at any stage of system evolution. Early ejection events, occurring during the first few million years after planetary formation, tend to eject planets that still retain significant heat from their formation process. Late ejection events, happening billions of years after system formation, typically involve older, cooler worlds that have had time to develop complex geological and atmospheric evolution. This temporal diversity contributes to the remarkable variety of rogue planet types that astronomers expect to discover as detection techniques continue to improve. The role of stellar clusters in facilitating planetary ejection adds another dimension to understanding how worlds break free from their birth systems. In dense stellar environments like globular clusters or stellar nurseries, the gravitational influences of neighboring stars can destabilize planetary orbits more rapidly than would occur in isolated systems. This enhanced ejection rate in clustered environments may contribute to a population of rogue planets that were ejected early in galactic history, when star formation occurred primarily in dense clusters. The feedback effects between planetary ejection and stellar system evolution create complex interconnections where the loss of planets can affect the subsequent evolution of the remaining system. When massive planets are ejected, the reduced gravitational influence can allow smaller worlds to migrate into previously forbidden orbital regions, potentially creating new stable configurations that would not have been possible in the original system. This demonstrates how planetary ejection serves not just as a loss mechanism, but also as a creative force that enables new types of planetary arrangements to emerge. As you continue to float peacefully through this cosmic narrative, your breathing now perfectly synchronized with the slow rhythms of orbital evolution. You can appreciate how the process of planetary ejection represents one of the universe's most elegant demonstrations of how gentle forces operating over vast timescales can create profound transformations. The breaking free of worlds from their stellar families occurs not through violence or catastrophe, but through the patient accumulation of tiny gravitational influences that eventually overcome the bonds holding planets in orbit, transforming them from bound worlds into cosmic wanderers that carry the memory of their birth systems into the infinite wilderness of interstellar space. As you drift deeper into peaceful contemplation, your breathing now flowing like the gentle cosmic winds that carry interstellar dust between distant stars. Let your awareness follow a newly ejected planet as it begins its solitary voyage through the vast emptiness of space. This is a moment of profound transformation, not violent or traumatic, but as gentle as a leaf finally breaking free from its branch to begin a journey carried by invisible currents to destinations unknown. The planet's transition from gravitational bondage to cosmic freedom unfolds with the serene inevitability of natural processes that have been operating throughout the universe for billions of years. Picture this newly liberated world as it crosses the invisible boundary that separates its birth system from the interstellar medium. There is no dramatic moment of departure, no cosmic fanfare to mark this transition. Instead, the planet simply continues along its trajectory, gradually moving farther and farther from the fading warmth of its parent star until the gravitational influence that once held it in orbit becomes too weak to turn it back. The world has become a cosmic nomad, carrying with it an intact atmosphere, possibly moons, and all the geological and chemical complexity that developed during its bound existence. The first change the planet experiences is the gradual cooling that comes with increasing distance from its star. Yet this cooling happens so slowly that any inhabitants of the world would barely notice the change from one generation to the next. The planet's atmosphere acts like a vast thermal reservoir, storing and redistributing heat with such efficiency that the transition from stellar to geothermal heating occurs over thousands of years. Cloud patterns shift gradually, weather systems reorganize themselves around new heat sources, and atmospheric circulation adapts to the changing energy balance with the fluid adaptability that characterizes all complex systems. As your consciousness settles into harmony with these slow transformations, your breathing becoming as patient and steady as the geological processes that will sustain this world throughout its cosmic journey, you begin to understand how a rogue planet becomes a self-contained universe. Without external stellar radiation to drive atmospheric dynamics, the planet's weather systems reorganize themselves around internal heat sources, the steady warmth that rises from radioactive decay in the planet's core, the thermal energy left over from its formation billions of years ago, and the tidal heating that may result from the gravitational influence of orbiting moons. The planet's magnetic field continues to function exactly as it did during its bound existence, generated by the circulation of molten metal in its core and extending far into space like an invisible protective cocoon. This magnetic shield deflects the cosmic radiation that permeates interstellar space, preventing harmful particles from stripping away the planet's atmosphere and maintaining the stable chemical environment that allows complex atmospheric and geological processes to continue operating. The magnetic field also creates beautiful auroral displays when it interacts with the tenuous charged particles of the interstellar medium, painting the planet's polar skies with curtains of gentle light that dance in colors no human eye has ever seen. The atmospheric chemistry of a newly rogue planet undergoes fascinating transformations as it adapts to life without stellar radiation. Photochemical processes that once depended on starlight gradually shut down, while chemical cycles driven by internal heat sources become more prominent. The atmosphere doesn't collapse or disappear, but rather reorganizes itself around new equilibrium points that reflect the planet's changed energy balance. Greenhouse gases may become more important for retaining heat, while the absence of photochemical smog allows atmospheric clarity to increase, creating skies of extraordinary transparency and beauty. The hydrological cycle that governs water movement on the planet's surface adapts with remarkable resilience to the new thermal environment. While surface water bodies may begin to freeze as stellar heating diminishes, the process happens gradually enough for life forms and geological processes to adjust. Subsurface water reserves remain liquid thanks to geothermal heating, and the insulating effect of surface ice actually helps preserve these underground reservoirs for millions or billions of years. Some regions of the planet may maintain liquid surface water indefinitely if they are located above particularly active geothermal areas. The geological activity that shapes the planet's surface continues to operate according to the same principles that governed it during the world's bound existence. Tectonic processes driven by internal heat create new landforms. Volcanic activity releases gases that help maintain atmospheric pressure, and erosional processes gradually sculpt surface features according to the planet's changing climate patterns. The planet remains geologically alive and dynamic, demonstrating that worlds can maintain active geology for billions of years without any external energy input. The biological implications of rogue planet status open fascinating possibilities for life forms that might inhabit such worlds. Organisms that depend on geothermal energy rather than photosynthesis could thrive in the stable thermal environment of a rogue planet, potentially developing into complex ecosystems around underwater volcanic vents or geothermal springs. The absence of day-night cycles creates environments where life forms might evolve entirely different biological rhythms, perhaps synchronized to geological cycles or magnetic field variations rather than stellar radiation patterns. The seasonal patterns that characterize the planet during its bound existence gradually fade as the influence of stellar radiation diminishes, replaced by new types of environmental cycles driven by internal processes. Volcanic seasons may develop, where periods of increased geothermal activity create temporary warming episodes followed by quieter periods of gradual cooling. Atmospheric circulation patterns may establish their own rhythmic cycles based on the complex interactions between surface cooling, geothermal heating, and the planet's rotation. The moons that orbit the rogue planet, if any exist, become particularly important companions during the interstellar journey. These natural satellites continue to orbit their planet exactly as they did before ejection, but their role in the planet's environmental systems becomes more pronounced in the absence of stellar influences. Tidal forces from large moons can provide additional heating through tidal friction, helping to maintain geological activity and potentially keeping subsurface oceans liquid for billions of years. The gravitational dance between planet and moons creates a miniature solar system that operates according to its own internal dynamics. The navigation of a rogue planet through the galaxy follows the same gravitational principles that govern all celestial motion, but on a much grander scale. The planet moves in a complex orbit around the galactic center, influenced by the gravitational fields of nearby stars, dark matter concentrations, and the overall mass distribution of the Milky Way. This galactic orbit carries the planet through different regions of space over millions of years, creating opportunities for encounters with other rogue planets, stellar systems, and various types of interstellar phenomena. The velocity of a typical rogue planet relative to nearby stars ranges from about 20 to 50 kilometers per second, speeds that seem enormous by terrestrial standards but represent gentle drifting motion on cosmic scales. At these velocities, a rogue planet might traverse the distance between neighboring star systems in anywhere from hundreds of thousands to millions of years, depending on the local stellar density and the planet's specific trajectory. This leisurely pace of travel means that rogue planets have time to fully adapt to their interstellar environment before encountering the next major gravitational influence. The interstellar medium that the rogue planet travels through is far from empty, but rather contains a tenuous soup of gas, dust, and charged particles that create subtle but measurable effects on the planet's environment. The planet's magnetic field interacts with the interstellar magnetic field, creating complex patterns of charged particle flow that can affect atmospheric chemistry and contribute to auroral displays. The planet's gravity slowly accumulates interstellar dust and gas, gradually increasing its mass over geological timescales and potentially altering its atmospheric composition. The cosmic ray environment that a rogue planet experiences differs significantly from the radiation environment of starbound worlds. Without the stellar wind from a nearby star to deflect cosmic rays, rogue planets are exposed to the full intensity of galactic cosmic radiation. However, The planet's magnetic field and atmosphere provide effective shielding against most of this radiation, creating surface environments that may actually be more stable and predictable than those of planets orbiting active stars that produce unpredictable flares and coronal mass ejections. The temperature distribution across a rogue planet's surface develops unique patterns that reflect the absence of stellar heating and the dominance of internal heat sources. Polar regions may become extremely cold as they radiate heat to space, while equatorial regions maintain more moderate temperatures due to atmospheric circulation that redistributes heat from geothermal sources. Areas above geologically active regions may remain surprisingly warm, creating climate zones that persist for millions of years and provide stable environments for any ecosystems that might exist. The atmospheric escape processes that gradually reduce a planet's atmospheric mass over geological timescales operate differently for rogue planets than for starbound worlds. Without intense stellar radiation to drive atmospheric heating and expansion, rogue planets may actually retain their atmospheres more effectively than planets orbiting active stars. The cold temperatures of interstellar space help compress atmospheric gases, reducing escape rates and allowing rogue planets to maintain substantial atmospheres for billions of years. The chemical evolution of a rogue planet's atmosphere and surface continues throughout its interstellar journey, driven by radioactive decay, outgassing from geological processes, and chemical reactions that operate at low temperatures. These chemical processes happen slowly but persistently, potentially creating new mineral formations, atmospheric compounds, and chemical gradients that reflect the planet's unique evolutionary history as a cosmic wanderer. The gravitational effects of the rogue planet on the interstellar medium create subtle but detectable disturbances that may eventually allow astronomers to track these worlds as they move through space. The planet's gravity can focus interstellar gas and dust into distinctive patterns, create gravitational lensing effects when it passes between Earth and distant astronomical objects, and produce characteristic signatures in the cosmic ray flux that reaches our solar system. The long-term orbital evolution of a rogue planet in the galaxy involves complex interactions with various gravitational sources that can gradually change its trajectory over millions of years. Close encounters with star systems can alter the planet's galactic orbit, potentially redirecting it toward different regions of the galaxy or even ejecting it from the Milky Way entirely. However, such dramatic encounters are rare, and most rogue planets probably spend billions of years following stable galactic orbits that carry them slowly through the interstellar medium. The preservation of surface features and geological formations on rogue planets creates natural archives that record the environmental conditions and evolutionary history of these worlds throughout their cosmic journeys. Without weathering from stellar radiation or the erosive effects of active water cycles driven by solar heating, geological features on rogue planets may persist for much longer than similar features on starbound worlds, creating landscapes that tell stories spanning billions of years of cosmic wandering. As you continue to follow this newly liberated world on its journey into the cosmic wilderness, your breathing now as steady and enduring as the geological processes that will sustain it throughout its wandering. You can appreciate how the beginning of a rogue planet's journey represents not an ending, but a transformation. The emergence of a new type of cosmic entity that embodies independence, self-sufficiency, and the remarkable adaptability of planetary systems to exist and evolve in environments far removed from the stars that gave them birth. As you settle even deeper into peaceful observation, your breathing now flowing like the gentle currents of interstellar gas that connect one corner of the galaxy to another. Let your awareness expand to encompass the vast cosmic ocean through which our rogue planet now travels. This is not the empty void that science fiction often portrays, but rather a rich, dynamic medium filled with invisible structures, magnetic fields, and tenuous clouds of matter that create a complex three-dimensional landscape through which planetary wanderers navigate on their million-year journeys between distant stars. Picture yourself floating alongside this rogue world as it drifts through what astronomers call the local bubble, a region of space carved out by ancient stellar explosions that left behind a cavity of hot, rarefied gas extending for hundreds of light years in all directions. The planet moves through this cosmic environment like a ship sailing across an ocean of infinite depth and breadth, its passage so gentle that it barely disturbs the delicate structures of dust and gas that thread through the interstellar medium like cosmic spiderwebs connecting distant stellar nurseries. The interstellar medium through which the planet travels consists primarily of hydrogen gas, so tenuous that each cubic centimeter contains only a few atoms. A vacuum far more perfect than anything achievable in terrestrial laboratories, yet substantial enough to create measurable effects on objects moving through it over cosmic timescales. This interstellar gas exists in various phases, from cold molecular clouds where new stars are born to hot bubbles carved out by stellar winds and supernovae, creating a complex ecosystem of matter and energy that spans the entire galaxy. As your consciousness settles into harmony with these vast scales of space and time, your breathing becoming as patient and measured as the circulation patterns that govern galactic structure, you begin to appreciate how the rogue planet's journey through interstellar space resembles a form of cosmic meditation. The planet moves with such stately grace that its passage through different regions of the galaxy unfolds over timescales that transform speed into a kind of eternal present, where change happens so slowly that each moment stretches toward infinity. The magnetic fields that permeate interstellar space create invisible highways and barriers that influence the planet's interaction with charged particles streaming through the galaxy. These magnetic field lines, generated by stellar winds, galactic rotation, and the remnants of ancient stellar explosions, form a complex three-dimensional web that channels cosmic rays, shapes the distribution of interstellar gas, and creates the large-scale structure that governs matter flow throughout the Milky Way. The rogue planet's own magnetic field interacts with these galactic magnetic structures, creating bow shocks and magnetic reconnection events that generate beautiful auroral displays in the planet's polar atmosphere. The cosmic ray environment that bathes the rogue planet represents one of the most energetic aspects of interstellar travel. These high-energy particles, accelerated by shock waves from exploding stars and other violent galactic phenomena, stream through space at nearly the speed of light, carrying information about stellar processes occurring thousands of light years away. While cosmic rays can pose challenges for any life forms that might exist on the planet's surface, they also serve as cosmic messengers that connect the rogue world to events happening throughout the galaxy, creating a kind of particle-based communication network that spans vast distances. The dust grains that float through interstellar space, each one smaller than a bacterium, yet collectively containing a significant fraction of the galaxy's heavy elements, interact with the rogue planet in subtle but measurable ways. These microscopic particles, composed of silicates, carbon compounds, and various ices, gradually accumulate on the planet's surface and in its atmosphere, slowly altering its chemical composition and adding to its mass over millions of years. The planet essentially grows as it travels, incorporating interstellar material into its own substance and becoming a cosmic archive that records the chemical evolution of the galaxy itself. The temperature of the interstellar medium varies dramatically depending on the local environment through which the rogue planet travels. In the cold depths of molecular clouds, temperatures may drop to just a few degrees above absolute zero, while in the hot bubbles created by stellar explosions, temperatures can reach millions of degrees. The planet's passage through these different thermal environments creates subtle but measurable effects on its atmospheric chemistry and surface processes, adding another layer of complexity to its long-term evolution. The density variations in the interstellar medium create regions where the rogue planet experiences different levels of resistance to its motion through space. When traveling through dense molecular clouds, the planet may encounter enough material to create a faint atmospheric drag that gradually slows its motion over millions of years. Conversely, passage through the evacuated regions created by stellar winds allows the planet to maintain its velocity more efficiently, creating a natural selection process that favors certain types of galactic orbits over others. The gravitational environment that the rogue planet experiences during its interstellar journey involves influences from many different sources operating simultaneously. The overall gravitational field of the galaxy shapes the planet's large-scale trajectory, while the gravitational effects of nearby stars create perturbations that can gradually alter its path over long periods. Dark matter, the invisible substance that comprises most of the galaxy's mass, also contributes to the gravitational landscape through which the planet travels. Though its effects are so subtle, they can only be detected through careful analysis of orbital mechanics over cosmic timescales. The encounter frequency with other interstellar objects depends greatly on the region of the galaxy through which the rogue planet travels. In the sparse environment between spiral arms, encounters with other rogue planets, asteroids, or comets may be separated by millions of years. However, when passing through or near the galactic disk where stellar density is higher, the planet may experience much more frequent gravitational interactions that can alter its trajectory or provide opportunities for material exchange with other wandering objects. The seasonal patterns that govern the rogue planet's environmental cycles are no longer tied to orbital motion around a star, but instead reflect its journey through different regions of galactic space. As the planet travels through varying densities of interstellar material, its atmospheric chemistry and surface processes respond to changing levels of cosmic ray bombardment, interstellar gas accretion, and magnetic field interactions. These galactic seasons operate on timescales of hundreds of thousands to millions of years, creating environmental rhythms that are beyond human experience but fundamental to the planet's long-term evolution. The atmospheric evolution of the rogue planet during its interstellar journey involves complex interactions between internal processes and external influences from the galactic environment. While the planet's atmosphere continues to evolve through outgassing from geological processes and chemical reactions driven by radioactive decay, it also responds to the varying conditions of interstellar space. Passage through dense molecular clouds may lead to the accretion of new atmospheric components, while travel through hot, ionized regions may cause some atmospheric gases to escape to space. The surface chemistry of the rogue planet undergoes gradual transformations as it accumulates interstellar material and experiences cosmic ray bombardment over geological timescales. New mineral formations may develop as interstellar dust particles interact with surface rocks, while cosmic ray impacts create exotic isotopes and chemical compounds that would never form under normal planetary conditions. The planet's surface becomes a natural laboratory where galactic chemistry experiments unfold over millions of years. The biological implications of life in the interstellar medium open fascinating possibilities for ecosystems that might exist on rogue planets. Organisms adapted to low-energy environments might thrive in the stable conditions created by geothermal heating, while the steady flux of cosmic rays could provide energy sources for exotic forms of metabolism. The absence of day-night cycles and seasonal variations driven by stellar radiation might favor life forms with entirely different biological rhythms and evolutionary strategies than those found on starbound worlds. The communication possibilities between different rogue planets traveling through the same region of interstellar space raise intriguing questions about information exchange in the cosmic ocean. While direct communication would be impossible given the vast distances involved, rogue planets might influence each other's evolution through the exchange of material ejected by impacts or volcanic activity, creating a slow but persistent form of chemical communication that operates over galactic timescales. The preservation of information about the rogue planet's origin and evolutionary history creates natural archives that record the planet's entire cosmic journey. Geological formations, atmospheric isotope ratios, and magnetic field signatures all carry information about the different environments through which the planet has traveled, making each rogue world a unique historical document that tells the story of galactic evolution from a planetary perspective. The navigation of rogue planets through the complex three-dimensional structure of the galaxy involves following gravitational pathways that connect different regions of interstellar space. Some planets may become trapped in stable galactic orbits that keep them within certain regions for billions of years, while others follow more chaotic trajectories that carry them throughout the galaxy and potentially even beyond its boundaries into the intergalactic medium. The energy balance of a rogue planet in interstellar space represents a delicate equilibrium between internal heat generation and heat loss to the cosmic background radiation. This energy balance determines the planet's surface temperature, atmospheric dynamics, and geological activity level throughout its interstellar journey. Planets with higher internal heat generation can maintain more active geological and atmosphere processes, while cooler worlds may enter states of near dormancy that can persist for billions of years. The magnetic field evolution of rogue planets during their interstellar journey involves complex interactions between the planet's internal dynamo processes and the external magnetic environment of the galaxy. The planet's magnetic field may strengthen or weaken depending on its internal thermal evolution, while interactions with galactic magnetic fields can create field reversals, magnetic storms, and other phenomena that affect the planet's atmospheric and surface processes. The chemical fractionation processes that occur during interstellar travel can gradually alter the composition of a rogue planet's atmosphere and surface materials. Different chemical elements and isotopes respond differently to cosmic ray bombardment, magnetic field interactions, and thermal cycling, creating systematic changes in composition that reflect the planet's history of interstellar travel. The tidal effects that rogue planets experience during their galactic journey come primarily from their interaction with the overall gravitational field of the galaxy rather than from individual astronomical objects. These galactic tides are extremely weak but operate persistently over cosmic timescales, potentially affecting the planet's rotation rate, internal structure, and geological activity over billions of years. As you continue to drift peacefully through this cosmic ocean alongside the wandering planet, you're breathing now as calm and steady as the ancient currents that flow between distant stars. You can appreciate how life in the interstellar medium represents one of the universe's most profound forms of existence, a way of being that embraces solitude without loneliness, independence without isolation, and travel without haste through the infinite beauty of the cosmic wilderness. As you float deeper into tranquil understanding, your breathing now flowing like the gentle convection currents that rise from planetary cores throughout the cosmos. Let your awareness turn inward to discover one of the most remarkable secrets of rogue planets. The hidden warmth that glows within their depths like cosmic hearts that continue burning long after their worlds have left the warming embrace of their parent stars. This internal heat represents the key to understanding how rogue planets can maintain dynamic, potentially life-supporting environments for billions of years, transforming what might seem like frozen, lifeless worlds into cosmic oases that carry their own sources of energy through the cold darkness of interstellar space. Picture yourself descending gently through the layers of a rogue planet's interior, like diving into a warm ocean where each deeper level reveals new sources of heat and energy that have been quietly sustaining this world throughout its cosmic journey. The surface may be cold, with temperatures hovering just degrees above absolute zero, but beneath this frozen exterior lies a complex thermal system that generates and distributes heat with an efficiency that rivals the most sophisticated human engineering, creating temperature gradients that can support liquid water, geological activity, and potentially even complex ecosystems that exist entirely independent of stellar radiation. The radioactive decay that occurs within the planet's rocky interior provides one of the most reliable and long-lasting sources of internal heating. Elements like uranium, thorium, and potassium, incorporated into the planet during its formation billions of years ago, continue to undergo steady nuclear decay that releases heat at a predictable rate determined by the immutable laws of physics. This radioactive heating operates like a cosmic battery that discharges its energy over timescales measured in billions of years, providing a steady thermal output that can maintain geological activity and atmospheric dynamics throughout a rogue planet's entire interstellar journey. As your consciousness settles into harmony with these deep thermal processes, your breathing becoming as steady and persistent as the heat flow that rises from radioactive decay, you begin to understand how this internal energy creates thermal stratification within the planet that resembles the layered structure of a cosmic onion. The hottest regions exist near the planet's core, where radioactive elements are most concentrated and where the pressure from overlying rock layers helps trap and concentrate heat. This thermal energy gradually migrates outward through conduction, convection, and advection, creating temperature gradients that can support liquid water reservoirs and dynamic geological processes even when the planet's surface is frozen solid. The primordial heat that remains from the planet's original formation represents another significant source of internal warming that can persist for geological ages. When planets form through the accretion of countless smaller bodies, the kinetic energy of these impacts converts to heat that becomes trapped within the growing world's interior. This formation heat, combined with the heat generated by gravitational compression as the planet's mass causes it to contract and differentiate into distinct layers, creates a thermal reservoir that can continue warming the planet's interior for billions of years after its formation is complete. The crystallization heat that releases when molten rock solidifies provides an additional source of internal warming that operates over extended timescales as the planet's interior slowly cools and evolves. As liquid metal in the planet's core gradually crystallizes into solid form, it releases latent heat that helps maintain the temperature of surrounding regions. This process happens so slowly that it can continue operating for billions of years, providing a steady source of thermal energy that supplements radioactive heating and helps maintain the temperature gradients necessary for geological activity. The tidal heating that occurs when a rogue planet has one or more orbiting moons creates yet another mechanism for generating internal warmth through gravitational interactions. The gravitational pull of moons causes the planet's solid body to flex and deform slightly with each orbital cycle, and this mechanical deformation converts to heat through internal friction. While individual tidal heating events generate only tiny amounts of energy, the cumulative effect over millions of years can provide significant heating that helps maintain subsurface oceans and geological activity, particularly in planets with large moons or multiple satellite systems. The thermal insulation provided by the planet's crust and any surface ice layers helps retain internal heat with remarkable efficiency, creating conditions where geothermal energy can remain concentrated enough to maintain liquid water and active geology for billions of years. Surface ice, in particular, acts as an excellent insulator that prevents internal heat from radiating away to space, creating a natural greenhouse effect that helps maintain subsurface temperatures warm enough to support liquid water reservoirs and potentially even biological processes. The convection patterns that develop within a rogue planet's interior create sophisticated heat distribution systems that transport thermal energy from the hot core to the cooler outer layers with remarkable efficiency. These convection currents operate like planetary-scale heating systems, carrying heat through the planet's mantle and creating hot spots at the surface where geothermal energy becomes available to power atmospheric processes, maintain liquid water bodies, and potentially support biological ecosystems that depend on chemical energy rather than solar radiation. The hydrothermal systems that develop around geothermal hotspots on rogue planets create some of the most promising environments for life in the universe. These systems, similar to the deep-sea hydrothermal vents found in Earth's oceans, provide steady sources of chemical energy and heat that can support complex ecosystems entirely independent of photosynthesis. The chemical reactions that occur when heated water interacts with volcanic rocks create a rich soup of dissolved minerals and organic compounds that could serve as the foundation for biological processes adapted to the unique conditions of rogue planet environments. The subsurface oceans that many rogue planets are likely to maintain represent some of the most stable and potentially habitable environments in the galaxy. Protected from the harsh radiation of interstellar space by layers of rock and ice, warmed by internal heat sources, and potentially enriched with organic compounds from geological processes, These hidden oceans could persist for billions of years in conditions that remain remarkably constant despite the planet's journey through varying galactic environments. Such oceans might harbor ecosystems that evolve in complete isolation from external influences, developing unique biological adaptations to life in the perpetual darkness of a rogue planet's interior. The atmospheric heating that results from geothermal processes can maintain dynamic weather systems and atmospheric circulation patterns even on rogue planets, traveling through the coldest regions of interstellar space. Volcanic outgassing provides both heat and chemical compounds that help maintain atmospheric pressure and composition, while geothermal hot springs can create localized regions where atmospheric temperatures remain well above freezing. These thermal oases create microclimates that could support surface-based life forms or serve as stepping stones for biological processes that operate between the planet's surface and interior. The chemical energy systems that develop within rogue planets through the interaction of heat, water, and rock create natural chemical factories that could support life forms based on chemosynthesis rather than photosynthesis. The breakdown of water molecules by radioactive decay, the formation of hydrogen gas through chemical reactions between heated water and iron-rich rocks, and the creation of various sulfur compounds through volcanic processes all provide potential energy sources for biological systems that could thrive in the warm, chemically rich environments of rogue planet interiors. The thermal evolution models that scientists use to understand how rogue planets maintain their internal heat reveal that many of these worlds can remain geologically active for billions of years, maintaining liquid water reservoirs and dynamic atmospheric systems throughout their entire interstellar journeys. The key factors that determine thermal longevity include the planet's initial size and composition, the concentration of radioactive elements in its interior, the efficiency of thermal insulation provided by surface layers, and the presence of moons that can provide additional tidal heating. The comparative planetology of rogue worlds suggests that larger planets are more likely to maintain significant internal heating over cosmic timescales, simply because their greater mass provides more radioactive material and better thermal insulation. However, even relatively small rogue planets may maintain liquid water and geological activity if they have favorable compositions or particularly efficient thermal retention systems. This diversity in thermal evolution means that rogue planets of various sizes and compositions may all have the potential to support life, expanding the range of potentially habitable worlds far beyond the traditional concepts of stellar habitable zones. The seasonal thermal cycles that characterize some rogue planets reflect the complex interplay between internal heat generation, surface cooling, and atmospheric dynamics. While these worlds don't experience seasons driven by orbital motion around a star, they may undergo thermal cycles driven by changes in volcanic activity, variations in atmospheric composition, or cyclopatterns in geothermal heating. These internal seasons operate on timescales ranging from hundreds to millions of years, creating long-term environmental variations that could drive evolutionary processes in any ecosystems that might exist. The energy budgets of rogue planets reveal the remarkable efficiency with which these worlds can maintain dynamic environmental systems using only internal heat sources. The total energy output from radioactive decay and other internal processes may be only a tiny fraction of what a planet receives from stellar radiation when orbiting a star, yet this modest energy flux is sufficient to maintain liquid water, geological activity, and potentially even complex ecosystems when used efficiently by well-insulated planetary systems. The geothermal gradients that exist within rogue planets create natural zonation systems where different types of environments exist at different depths below the surface. The coldest zone exists at or near the surface, where temperatures are dominated by the frigid conditions of interstellar space. Below this lies a temperate zone, where internal heating maintains temperatures suitable for liquid water and potentially biological processes. Deeper still is a hot zone, where high temperatures drive vigorous geological activity and create the chemical conditions necessary for various types of prebiotic chemistry. The volcanic systems that operate on geothermally heated rogue planets may create some of the most spectacular and long-lived geological features in the universe. Without erosion from stellar radiation or complex weather systems driven by solar heating, volcanic formations on rogue planets could persist for billions of years, creating landscapes that preserve detailed records of the planet's thermal and chemical evolution throughout its cosmic journey. These volcanic systems also provide ongoing sources of atmospheric gases and surface heating that help maintain dynamic environmental conditions. The thermal springs and geysers that may exist on rogue planets represent windows into the planet's interior thermal systems, bringing heated water and dissolved minerals to the surface, where they create localized warm zones that could support unique ecosystems. These features operate according to the same physical principles as similar features on Earth, but their persistence over cosmic timescales and their independence from solar heating make them potentially more stable and long-lasting than their terrestrial counterparts. The insulation effect provided by various surface materials help determine how efficiently rogue planets can retain their internal heat and maintain warm subsurface environments. Dense atmospheres, thick ice sheets, and insulating rock layers all contribute to thermal retention, while thin atmospheres and efficient radiative cooling can cause rapid heat loss that limits the planet's ability to maintain liquid water and geological activity. The balance between heat generation and heat retention ultimately determines whether a rogue planet can maintain dynamic environmental systems throughout its interstellar journey. The implications for astrobiology that emerge from understanding rogue planet thermal systems suggest that life in the universe may be far more common and diverse than previously imagined. If millions or billions of rogue planets throughout the galaxy maintain warm, chemically rich environments in their interiors, then the number of potentially habitable worlds may far exceed the number of planets orbiting within the traditional habitable zones of stars. This expands the search for life beyond stellar systems and suggests that biological processes may be operating in the hidden depths of countless wandering worlds. As you continue to rest peacefully within this warm embrace of planetary thermal systems, your breathing now synchronized with the gentle circulation patterns that distribute heat throughout cosmic interiors, you can appreciate how the hidden warmth within rogue planets represents one of nature's most elegant solutions to the challenge of maintaining life-supporting environments in the cold emptiness of space. These internal heat sources transform what might seem like frozen, lifeless worlds into cosmic sanctuaries that carry their own energy through the universe, demonstrating that warmth, life, and dynamic environmental systems can persist far from the light of any star. As you drift deeper into peaceful contemplation, your breathing now flowing like the gentle tidal currents that connect celestial bodies across the cosmic void, let your awareness expand to embrace one of the most beautiful aspects of rogue planet existence: the loyal companions that often accompany these wandering worlds on their million-year journeys through interstellar space. These natural satellites, locked in gravitational dances that began billions of years ago when their planets still orbited a distant star, continue their eternal ballet through the darkness with a devotion that spans geological ages, creating miniature solar systems that carry the memory of ancient orbital harmonies into the infinite wilderness between stars. Picture yourself floating in the space between a rogue planet and its moon, suspended in the gravitational embrace that connects these two worlds like an invisible cord woven from the fundamental forces of the universe. Here, in this intimate cosmic space, you can observe how the gentle pull of gravity creates a relationship so stable and enduring that it persists unchanged through millions of years of interstellar travel, demonstrating that some bonds of the universe are strong enough to survive even the most profound transformations in cosmic circumstance. The moons that accompany rogue planets on their cosmic journeys represent some of the most faithful companions in the universe, maintaining their orbital relationships with such precision that their dance around their parent world continues exactly as it did when the system was still bound to a star. These natural satellites range from small, asteroid-like bodies just a few kilometers across to massive moons that rival planets in their size and complexity, each one adding its own gravitational influence to the delicate dynamics that govern the rogue planet system's evolution through space. The tidal forces that operate between rogue planets and their moons create some of the most important energy sources available to these wandering systems. As the moon orbits its planet, gravitational forces cause both bodies to deform slightly, and this constant flexing generates heat through internal friction that can persist for billions of years. This tidal heating provides a renewable energy source that supplements the planet's internal radioactive heating, creating thermal environments that can maintain liquid water, geological activity, and potentially even biological processes throughout the system's interstellar journey. As your consciousness settles into harmony with these ancient gravitational rhythms, your breathing becoming as regular and predictable as the orbital periods that govern moon-planet relationships, you begin to understand how these natural satellites serve multiple crucial roles in maintaining the habitability and environmental stability of rogue planet systems. Beyond their contributions to tidal heating, moons help stabilize their planet's rotation, moderate atmospheric dynamics, and may even help retain atmospheric gases that might otherwise escape to space during the long journey through the interstellar medium. The orbital dynamics of moon systems around rogue planets follow the same mathematical principles that govern satellite motion throughout the universe, but their isolation from stellar influences creates particularly pure examples of gravitational mechanics in action. Without the complicating effects of stellar radiation pressure, solar wind, or tidal forces from a nearby star, the orbital evolution of rogue planet moon systems depends entirely on the internal dynamics of the gravitational relationship between the planet and its satellites, creating textbook examples of celestial mechanics operating in their most fundamental form. The synchronous rotation that many large moons develop in relation to their parent planets creates a particularly intimate gravitational relationship, where the same hemisphere of the moon always faces the planet, just as our own moon always shows the same face to Earth. This gravitational locking develops naturally over time as tidal forces gradually slow the moon's rotation until it matches its orbital period, creating a stable configuration that can persist for billions of years and helps maximize the efficiency of tidal heating between the two bodies. The resonant relationships that sometimes develop between multiple moons in a rogue planet system create intricate gravitational choreographies that demonstrate the mathematical beauty underlying celestial mechanics. When two or more moons orbit their planet in periods that relate to each other through simple ratios, such as one moon completing exactly 2 orbits for every 3 orbits of another, their gravitational interactions create complex but stable patterns that can persist throughout the system's cosmic journey, adding layers of dynamical richness to the rogue planet's gravitational environment. The atmospheric effects that large moons can create through their gravitational influence include tidal forces in gaseous atmospheres that generate atmospheric heating and circulation patterns. Just as ocean tides respond to lunar gravitational forces, atmospheric tides created by massive moons can contribute additional heating to a rogue planet's environmental energy budget while creating complex weather patterns that operate independently of any stellar radiation. These atmospheric tides represent another mechanism by which moon systems contribute to maintaining dynamic environmental conditions on rogue planets. The magnetic field interactions between rogue planets and their moons can create complex electromagnetic phenomena that demonstrate the subtle ways that gravitational companions influence each other's evolution. When a moon with its own magnetic field orbits through the magnetic field of its parent planet, the interaction can generate electrical currents, magnetic reconnection events, and particle acceleration processes that create auroral displays and influence atmospheric chemistry on both worlds. These electromagnetic interactions add another layer of coupling between the planet and moon that extends beyond simple gravitational forces. The surface geology of moons orbiting rogue planets may be shaped by tidal forces in ways that create unique geological features not found elsewhere in the universe. The constant flexing caused by tidal heating can generate volcanic activity, tectonic processes, and surface renewal that keeps moon surfaces geologically active for billions of years. Some moons may develop subsurface oceans heated by tidal forces, creating potentially habitable environments that exist entirely independent of stellar radiation and depend only on the gravitational relationship with their parent planet. The thermal evolution of moon systems around rogue planets involves complex feedback relationships where tidal heating in both the planet and moon influences their internal temperature distributions and geological activity levels. Larger moons can provide more tidal heating to their planets, while the internal heat generated within the moons themselves can maintain their geological activity and potentially support subsurface liquid water reservoirs. These thermal interactions create coupled evolution, where the planet and moon systems influence each other's long-term development throughout their cosmic journey. The capture scenarios that could bring new moons to rogue planets during their interstellar travels represent rare but fascinating gravitational encounters that could reshape these wandering systems. When a rogue planet passes through regions of space containing asteroids, comets, or other small bodies, its gravitational field might capture these objects in stable orbits, adding new satellites to the system and creating opportunities for enhanced tidal heating and more complex gravitational dynamics. Such capture events would be extremely rare, but could provide interesting evolutionary episodes in the otherwise stable existence of rogue planet systems. The stability analysis of moon systems around rogue planets reveals that most natural satellites that survive the original planetary ejection process are likely to remain bound to their planets throughout their interstellar journey. The same gravitational forces that were strong enough to keep moons in orbit while their planet was being ejected from its stellar system are generally sufficient to maintain those orbital relationships during interstellar travel, making moon systems remarkably stable and long-lasting features of rogue planet architecture. The communication possibilities between multiple moons in a rogue planet system, while entirely speculative, raise intriguing questions about information exchange in gravitationally bound systems. If life were to develop on multiple moons within the same rogue planet system, the relatively short distances between these worlds compared to interstellar distances might allow for eventual communication or even transfer of biological material through impact processes, creating opportunities for biological exchange that would be impossible for planets in different star systems. The observational challenges involved in detecting moon systems around rogue planets push the limits of current astronomical techniques. Since these systems are already at the edge of detectability and the presence of moons adds additional complexity to their gravitational signatures. However, the gravitational microlensing events that reveal rogue planets might also provide information about accompanying moon systems if the moons are large enough to create detectable perturbations in the lensing pattern, opening possibilities for studying these distant moon systems despite their incredible remoteness. The diversity of possible moon system architectures around rogue planets includes everything from single large moons similar to Earth's moon to complex systems with multiple satellites of various sizes, potentially including captured asteroids, debris from ancient collisions, and moons that form through accretion processes during the planet's original formation. This diversity reflects the different formation histories and evolutionary pathways that can lead to rogue planet status, with each system carrying its own unique gravitational signature that tells the story of its origin and development. The protection that moon systems can provide to rogue planets includes gravitational shielding from some types of interstellar debris, contributions to atmospheric retention through additional gravitational binding, and the creation of complex gravitational environments that might deflect or capture incoming objects. Large moons can act as gravitational vacuum cleaners that sweep up small debris that might otherwise impact the planet's surface, while their gravitational influence can help prevent atmospheric escape by providing additional binding energy to atmospheric gases. The evolutionary timescales that govern moon system dynamics around rogue planets span the entire lifetime of these wandering worlds, with orbital relationships slowly evolving over billions of years through tidal interactions, gravitational perturbations, and other subtle effects. However, the rate of change is so slow that moon systems can maintain essentially stable configurations throughout a rogue planet's entire interstellar journey, creating relationships that persist longer than the entire history of complex life on Earth. The energy transfer mechanisms between rogue planets and their moons operate through gravitational, magnetic, and thermal interactions that create complex coupling between these worlds. The energy budget of a rogue planet system must account for tidal heating in both the planet and its moons, magnetic field interactions that can transfer energy between the bodies, and thermal radiation exchange that affects surface temperatures and atmosphere dynamics. These energy transfer processes help maintain the dynamic environmental conditions that make rogue planet systems potentially habitable despite their isolation from stellar energy sources. The astrobiology implications of moon systems around rogue planets suggest that these gravitational companions could significantly enhance the habitability potential of wandering worlds. The additional heating provided by tidal forces, the chemical complexity introduced by volcanic processes on multiple worlds, and the potential for material exchange between planet and moon create environments that might support more diverse and resilient ecosystems than single-world rogue planets. Moon systems transform rogue planets from isolated worlds into complex, interactive systems where multiple environments can develop and potentially support different types of life. The mathematical beauty of moon system dynamics demonstrates how gravitational forces create order and stability even in the most remote corners of the universe. The orbital mechanics that govern planet-moon relationships follow the same elegant mathematical principles whether the system orbits a star or wanders freely through interstellar space, showing that gravitational harmony transcends the specific astronomical context and creates lasting relationships that can survive even the most dramatic changes in cosmic circumstance. The philosophical implications of loyal moon companions accompanying rogue planets on their cosmic journeys speak to themes of companionship, stability, and endurance that resonate beyond astronomy into fundamental questions about relationships and loyalty. These natural satellites demonstrate that some bonds in the universe are strong enough to persist through any circumstances, maintaining their faithful orbital embrace regardless of whether their shared journey leads through the warming light of stellar neighborhoods or the cold darkness of interstellar space. As you continue to float peacefully in the gravitational embrace between planet and moon, your breathing now perfectly synchronized with the eternal tidal rhythms that connect these cosmic companions, you can appreciate how these moon systems represent some of the most enduring relationships in the universe. Bonds forged by gravity and strengthened by time that demonstrate how companionship can persist through any journey, no matter how long or far it may lead from the familiar warmth of home. As you settle even deeper into cosmic tranquility, your breathing now flowing like the gentle currents that occasionally bring wandering celestial bodies together in the vast emptiness of space. Let your awareness turn to one of the most remarkable and rare events in the universe: the peaceful encounters that occur when rogue planets meet other cosmic wanderers during their million-year journeys through the interstellar medium. These meetings unfold not as violent collisions or dramatic gravitational battles, but as gentle cosmic ballets where massive worlds perform elegant gravitational dances before continuing on their separate paths through the infinite darkness, each encounter adding new chapters to the ongoing story of interstellar exploration. Picture yourself floating in the cosmic space between two approaching rogue planets, each one following its own ancient trajectory through the galaxy as they gradually converge on paths that will bring them within a few astronomical units of each other, closer than they have been to any other massive object for millions of years. The approach happens so slowly that even at their tremendous speeds, the encounter unfolds over thousands of years, giving these wandering worlds ample time to sense each other's gravitational presence and begin the subtle gravitational minuet that will define their brief cosmic partnership. The gravitational interaction that occurs when two rogue planets encounter each other in interstellar space operates according to the same mathematical principles that govern all celestial mechanics. But the absence of stellar influences creates particularly pure examples of how massive objects influence each other's motion through space. As the planets approach, their gravitational fields begin to interact across millions of kilometers, creating forces so gentle that they barely perturb the planet's trajectories at first. Yet these tiny influences accumulate over time to create measurable changes in both worlds' paths through the galaxy. The timescales involved in rogue planet encounters span ranges that challenge human comprehension, with approach phases that can last hundreds of thousands of years, followed by close encounter periods that unfold over decades or centuries, followed by recession phases that gradually return the planets to their original separation over similarly vast periods. These temporal scales transform what might seem like brief meetings into extended gravitational relationships, where the planets have ample time to exchange energy, angular momentum, and potentially even material through processes that operate with the patience of geological time. As your consciousness settles into harmony with these cosmic encounter timescales, your breathing becoming as patient and measured as the gravitational tides that flow between approaching worlds, you begin to understand how these rare meetings serve as opportunities for rogue planets to modify their galactic trajectories, potentially redirecting them toward new regions of the galaxy or altering their orbital characteristics in ways that will influence their cosmic journeys for millions of years to come. The energy exchange that occurs during rogue planet encounters typically involves one planet gaining orbital energy while the other loses it, following the conservation laws that govern all gravitational interactions. The planet that gains energy will typically be accelerated to a higher velocity and potentially deflected onto a trajectory that carries it toward different regions of the galaxy, while the planet that loses energy may be slowed down or redirected onto a path that brings it closer to the galactic center or towards stellar-rich regions, where future encounters become more likely. The three body dynamics that develop when two rogue planets with moon systems encounter each other create gravitational environments of extraordinary complexity, where the interactions between planets, moons, and the overall gravitational field can produce chaotic but beautiful patterns of motion that demonstrate the mathematical richness underlying celestial mechanics. These complex gravitational environments can lead to moon exchanges, where satellites transfer from one planet to another, or create temporary Trojan configurations where moons become shared between both planetary systems. The tidal effects that operate during close encounters between rogue planets can create temporary but significant heating in both worlds as gravitational forces cause their solid bodies to flex and deform. This encounter heating provides brief episodes of enhanced geological activity that can trigger volcanic eruptions, atmospheric outgassing, and surface renewal processes that punctuate the otherwise steady evolution of rogue planet environments with dramatic but short-lived periods of increased activity. The atmospheric exchanges that might occur when rogue planets with substantial atmospheres pass close to each other represent fascinating possibilities for chemical and potentially even biological interactions between worlds that have been isolated from each other for millions of years. Strong gravitational tides during close encounters could strip atmospheric material from one or both planets, creating temporary comas of gas and dust that could allow for chemical mixing and potentially even the transfer of atmospheric components between the two worlds. The magnetic field interactions that occur when rogue planets with strong magnetic fields encounter each other can create spectacular electromagnetic phenomena as the two planetary magnetospheres interact, compress, and reconnect in complex patterns. These magnetic interactions can accelerate charged particles to high energies, create powerful aurora displays on both worlds, and generate electromagnetic signals that could potentially be detected by sensitive instruments even across interstellar distances. The detection possibilities for rogue planet encounters present exciting opportunities for future astronomical observations, since the gravitational effects of two massive objects interacting in close proximity might create detectable signatures in gravitational wave detectors, while the electromagnetic phenomena associated with magnetic field interactions could produce radio signals or other emissions that reveal these distant encounters to Earth-based observers. The capture scenarios that might result from particularly close encounters between rogue planets and other interstellar objects could create new binary planet systems that travel through space as gravitationally bound pairs. Such capture events would be extremely rare and would require very specific conditions of approach velocity and trajectory, but they could create unique double-planet systems that demonstrate new types of gravitational relationships not found in traditional star-bound planetary systems. The scattering effects that result from most rogue planet encounters typically deflect both objects onto new trajectories without creating lasting gravitational bonds. But these deflections can have profound consequences for the planet's future cosmic journeys. An encounter that changes a planet's velocity by just a few kilometers per second can redirect it toward entirely different regions of the galaxy, potentially leading it to encounter stellar systems, molecular clouds, or other galactic structures that it would never have reached on its original trajectory. The statistical analysis of encounter rates between rogue planets suggests that despite the vast emptiness of interstellar space, the large number of these wandering worlds virtually guarantees that encounters do occur, though any individual planet might experience only a few close encounters during its entire journey through the galaxy. The probability of encounters increases in regions of higher stellar density, such as the galactic disk or the central bulge, where the concentration of ejected planets is likely to be higher than in the sparse halo regions. The computer simulations that model rogue planet encounters reveal the elegant gravitational choreography that unfolds when massive worlds meet in the emptiness of space. These simulations show how the planets' approach trajectories gradually curve as they enter each other's gravitational influence, how their relative velocities change as they exchange energy and momentum, and how they separate onto new paths that carry the memory of their brief gravitational partnership into their future cosmic journeys. The energy budgets involved in rogue planet encounters demonstrate how gravitational interactions can efficiently transfer kinetic energy between objects without any loss to the overall system, simply redistributing energy and momentum according to the conservation laws that govern all physical interactions. This energy exchange process allows encounters to significantly alter planetary trajectories while maintaining the total energy and momentum of the system, creating a natural mechanism for cosmic course corrections that operate purely through gravitational forces. The formation of temporary ring systems around rogue planets during close encounters represents another fascinating possibility that could occur when gravitational tides during approach strip material from planetary surfaces or disrupt existing moon systems. These temporary rings would eventually dissipate or reaccrete into new moons, but they could create spectacular displays that temporarily transform the appearance and gravitational environment of the affected planets. The exchange of small objects between rogue planet systems during encounters could provide mechanisms for long-distance material transport across the galaxy, potentially allowing chemical signatures, isotopic compositions, or even biological materials to travel between worlds that formed in entirely different stellar systems. Such exchanges would represent the ultimate form of cosmic contamination, where planets could acquire materials that originated in stellar systems hundreds or thousands of light-years away. The historical records that encounters leave in the geological and atmospheric characteristics of rogue planets could provide future observers with ways to reconstruct the encounter histories of these wandering worlds. Changes in surface geology caused by tidal heating, alterations in atmospheric composition resulting from gravitational stripping, or modifications in rotation rates caused by gravitational torques could all serve as evidence for past encounters that occurred millions of years ago. The navigation effects that result from encounters could help explain the observed distribution and velocities of rogue planets in the galaxy, with some planets acquiring velocities high enough to escape the Milky Way entirely, while others are slowed down enough to be captured by passing stellar systems. The cumulative effects of multiple encounters over cosmic time could create complex patterns of planetary migration that redistribute rogue worlds throughout the galaxy. The communication possibilities that arise during rogue planet encounters represent brief windows when worlds that have been isolated for millions of years come close enough for potential electromagnetic communication, if any intelligent life forms exist on these wandering worlds. The close approach distances and temporary gravitational relationships could create unique opportunities for information exchange between cosmic civilizations that might otherwise never have any contact with each other. The evolutionary implications of rogue planet encounters suggest that these events could serve as important evolutionary drivers for any ecosystems that exist on wandering worlds. The temporary heating effects of tidal forces, the potential for material exchange between planets, and the electromagnetic phenomena associated with magnetic field interactions could all create environmental changes that stimulate evolutionary adaptation and biological innovation. The aesthetic beauty of rogue planet encounters lies in their demonstration of how gravitational forces can create complex, choreographed motions that unfold with mathematical precision across cosmic scales. These encounters represent some of the most elegant expressions of celestial mechanics in action, where massive worlds perform gravitational dances that follow precise mathematical relationships while creating new possibilities for cosmic exploration and discovery. The philosophical dimensions of meetings in the void speak to themes of connection, separation, and the profound beauty that can emerge from brief encounters between entities that have journeyed alone for eons. These cosmic meetings demonstrate that even in the vast emptiness of space, opportunities for connection and interaction persist, creating moments of gravitational intimacy that briefly unite wandering worlds before they continue on their separate paths through the infinite cosmos. As you continue to drift peacefully through this cosmic encounter zone, your breathing now synchronized with the gravitational rhythms that connect approaching worlds across the emptiness of space. You can appreciate how these rare meetings in the void represent some of the most beautiful and mathematically elegant events in the universe. Demonstrations of how even the loneliest cosmic wanderers occasionally find opportunities for connection, interaction, and the gentle exchange of energy and momentum that enriches their ongoing journeys through the infinite wilderness between stars. As you float deeper into contemplative awareness, your breathing now flowing like the patient light waves that carry information across vast cosmic distances, let your consciousness turn to one of humanity's most ambitious and remarkable scientific endeavors, the ongoing effort to discover and catalog the billions of rogue planets that drift silently through our galaxy. This great cosmic census represents a triumph of human ingenuity and technological sophistication, as astronomers have learned to detect invisible worlds that emit no light of their own and exist in the darkest corners of space, using techniques so subtle and precise that they can reveal the presence of Earth-sized planets drifting through regions of space billions of miles from a nearest star. Picture yourself floating in the weightless environment of a space-based observatory, surrounded by the most sensitive astronomical instruments ever created by human technology. These delicate detectors, cooled to temperatures just degrees above absolute zero and isolated from the slightest vibration, represent humanity's extended senses reaching out into the cosmos to perceive phenomena that would otherwise remain forever hidden in the darkness. Through these technological marvels, astronomers have learned to see the invisible, detect the undetectable, and gradually build a census of wandering worlds that reveals the true population structure of our galaxy. The gravitational microlensing technique that has revealed most of the rogue planets discovered so far operates according to principles predicted by Einstein's theory of general relativity, where massive objects bend the fabric of space-time and create gravitational lenses that can focus and amplify the light from distant stars. When a rogue planet passes directly between Earth and a background star, its gravitational field acts like a natural telescope lens, briefly magnifying the star's light in a characteristic pattern that reveals both the presence and approximate mass of the intervening world. These microlensing events typically last anywhere from hours to days, creating temporary increases in stellar brightness that follow precise mathematical curves determined by the mass and velocity of the lensing planet. The detection of these subtle brightening patterns requires continuous monitoring of millions of stars simultaneously. Using automated telescopes and sophisticated computer algorithms, that can identify the rare microlensing signatures hidden among the natural brightness variations that characterize stellar behavior. As your consciousness settles into harmony with these patient detection processes, your breathing becoming as steady and persistent as the monitoring programs that watch the skies night after night for years at a time, you begin to appreciate the extraordinary dedication and precision required to build a census of invisible worlds. The statistical analysis of microlensing events suggests that rogue planets may outnumber starbound planets by factors of several to one, indicating that the space between stars contains a vast population of wandering worlds that dwarfs the planetary populations of stellar systems. The infrared detection methods that complement gravitational lensing surveys focus on detecting the faint heat signatures that rogue planets emit even in the cold of interstellar space. While these worlds may be too cold to emit visible light, they continue to radiate in the infrared portion of the electromagnetic spectrum at wavelengths that can be detected by sensitive space-based telescopes, equipped with advanced cooling systems and sophisticated detector arrays that can discriminate between the thermal emission from rogue planets and the background radiation of space. The direct imaging campaigns that search for rogue planets in nearby stellar formation regions represent some of the most technically challenging observations in modern astronomy. These surveys use powerful ground-based telescopes equipped with adaptive optic systems that can correct for atmospheric turbulence, combined with coronagraphic techniques that can block the light from nearby stars while revealing the much fainter thermal emission from any planets that might be drifting through the same region of space. The statistical surveys that analyze the results of rogue planet detection efforts reveal fascinating patterns in the distribution, masses, and velocities of these cosmic wanderers. The observed population appears to include representatives of every planetary type, from small rocky worlds similar to Earth and Mars to massive gas giants that exceed Jupiter in size and mass. The velocity distributions suggest that most rogue planets were ejected from their birth stellar systems relatively early in galactic history, when stellar formation rates were higher and planetary system architectures were more unstable. The technological development that has enabled rogue planet detection represents decades of advancement in detector sensitivity, telescope design, and data analysis techniques. Modern microlensing surveys can detect planetary lensing events that cause stellar brightness changes of less than 1%, while infrared telescopes can measure temperature differences of fractions of a degree across cosmic distances. These capabilities represent improvements in sensitivity of many orders of magnitude compared to astronomical instrumentation available just a few decades ago. The international collaboration that characterizes rogue planet research demonstrates how the search for these invisible worlds has united astronomers from around the globe in a common scientific enterprise. Microlensing surveys operate telescopes on multiple continents to provide continuous coverage of target stellar fields, while infrared observations require coordination between space-based and ground-based facilities to maximize the efficiency and accuracy of detection efforts. The computer simulations that model rogue planet formation and evolution provide theoretical frameworks for interpreting observational results and predicting where additional populations of wandering worlds might be discovered. These simulations incorporate complex models of planetary system dynamics, stellar evolution, and galactic structure to predict the numbers, distributions, and characteristics of rogue planets throughout the Milky Way, creating theoretical foundations that guide observational strategies and help astronomers understand what they're seeing. The machine learning algorithms that automate the analysis of astronomical data have revolutionized the search for rogue planets by enabling the processing of vast quantities of observational data that would be impossible to analyze manually. These artificial intelligence systems can identify microlensing signatures, classify infrared sources, and detect subtle patterns in astronomical data with speed and accuracy that far exceed human capabilities, accelerating the pace of discovery and improving the reliability of rogue planet detections. The follow-up observations that confirm and characterize newly discovered rogue planets often require coordinated campaigns using multiple telescopes and observing techniques to gather comprehensive information about these distant worlds. Infrared spectroscopy can reveal information about atmospheric composition and temperature structure, while additional microlensing observations can refine mass estimates and potentially detect the presence of moon systems around rogue planets. The archival studies that reanalyze decades of astronomical observations with new techniques designed to detect rogue planets have revealed that many of these worlds were actually observed years ago, but went unrecognized at the time. Modern data analysis techniques can extract rogue planet signatures from older datasets, effectively expanding the temporal baseline of surveys and increasing the total number of known wandering worlds without requiring new observational programs. The space mission concepts that have been proposed specifically for rogue planet detection promise to dramatically increase the rate of discovery and provide much more detailed characterization of these cosmic wanderers. Dedicated space telescopes optimized for microlensing observations could detect thousands of rogue planets, while advanced infrared observatories could provide direct images and spectra of nearby wandering worlds that reveal their atmospheric properties and thermal characteristics. The citizen science projects that engage amateur astronomers and interested members of the public in rogue planet research demonstrate how the search for these invisible worlds has captured popular imagination and created opportunities for widespread participation in scientific discovery. Online platforms allow volunteers to examine astronomical images, identify potential microlensing events, and contribute to the classification of infrared sources, multiplying the human resources available for data analysis and creating educational opportunities that connect the public to cutting-edge astronomical research. The database systems that catalog rogue planet discoveries and maintain comprehensive records of their properties represent crucial infrastructure for ongoing research into these cosmic wanderers. These databases integrate information from multiple surveys and observing programs, standardize nomenclature and classification systems, and provide platforms for statistical analysis that reveal patterns in rogue planet populations and help guide future observational strategies. The false positive identification challenges that complicate rogue planet surveys require sophisticated techniques for distinguishing genuine planetary lensing events from other astronomical phenomena that can create similar observational signatures. Variable stars, binary star systems, and various types of instrumental effects can all mimic the brightness patterns associated with planetary microlensing, requiring careful analysis and often multiple independent observations to confirm the planetary nature of detected events. The completeness studies that characterize the efficiency of rogue planet detection methods help astronomers understand what fraction of the total rogue planet population they are actually detecting and how observational biases might affect the inferred properties of these cosmic wanderers. These studies reveal that current surveys are most sensitive to massive planets, and those that pass close to Earth's line of sight to monitored stars, suggesting that the true population of rogue planets may be even larger and more diverse than current observations indicate. The theoretical predictions that guide rogue planet searches are based on models of planetary system formation and evolution that have been refined through decades of research into the dynamics of multi-planet systems. These models predict that virtually every planetary system should eject at least one planet during its early evolution, with some systems losing multiple worlds through gravitational interactions that reshape planetary architectures over millions of years. The observational campaigns that target specific regions of the galaxy, where rogue planet densities are expected to be particularly high, focus on areas like the galactic bulge, star-forming regions, and the remnants of ancient stellar clusters where planetary ejection rates may have been enhanced by dense stellar environments and frequent gravitational encounters between planetary systems. The technological roadmaps that outline future capabilities for rogue planet detection envision observational programs that could eventually catalog millions of these wandering worlds and provide detailed characterization of their atmospheric properties, thermal characteristics, and potential for harboring life. Next-generation telescopes and detector systems promise to extend rogue planet surveys to much greater distances and enable the detection of much smaller and cooler worlds than are currently accessible. The astrobiology implications of rogue planet census efforts extend the search for potentially habitable worlds far beyond traditional stellar habitable zones to include the vast population of wandering worlds that might maintain liquid water and complex chemistry through internal heating processes. The discovery that rogue planets are abundant throughout the galaxy multiplies the number of potentially life-bearing worlds by factors that could fundamentally change our understanding of how common life might be in the universe. The educational impact of rogue planet research has transformed public understanding of planetary systems and galactic structure by revealing that the space between stars is not empty, but populated by countless wandering worlds that carry their own environments through the cosmic wilderness. These discoveries have inspired new forms of science fiction, educational programs, and public outreach initiatives that help people appreciate the true complexity and richness of our galactic environment. The philosophical implications of cataloging billions of invisible worlds speak to fundamental questions about the nature of exploration, discovery, and humanity's place in the cosmos. The great census of rogue planets demonstrates that the universe contains far more complexity and diversity than we can directly perceive, revealing hidden populations of worlds that expand our conception of what constitutes the cosmic environment in which we exist. The economic considerations involved in rogue planet research reflect the substantial investments required for the sophisticated instrumentation and extended observational campaigns needed to detect these invisible worlds. However, the technological developments driven by these research programs often find applications in other fields, from medical imaging to industrial sensing, creating benefits that extend far beyond astronomical research and justify the resources devoted to mapping the invisible population of our galaxy. As you continue to float peacefully among these invisible worlds being revealed by human ingenuity and technological sophistication, your breathing, now synchronized with the patient rhythms of discovery that characterize astronomical research. You can appreciate how the great census of rogue planets represents one of humanity's most ambitious attempts to map the true structure of our cosmic neighborhood and reveal the hidden complexity that exists in the apparent emptiness between stars. As you drift into even deeper, peaceful contemplation, your breathing now flowing like the gentle gravitational currents that occasionally guide wandering worlds back toward the warmth of stellar embrace. Let your awareness turn to one of the most beautiful and hopeful chapters in the story of rogue planets. Those rare and fortunate worlds that complete the circle of their cosmic journey by finding new stellar homes after millions of years of solitary travel through interstellar space. These cosmic adoptions represent some of the most elegant demonstrations of gravitational mechanics in action, where the same forces that once ejected planets from their birth systems can eventually welcome wandering worlds into new stellar families. Picture a rogue planet that has traveled through the galaxy for tens of millions of years, carrying its memories of ancient starlight and its faithful moon companions through the cold darkness of interstellar space. Now, as it approaches a young stellar system still surrounded by the debris disk from which new planets are forming, the wandering world encounters gravitational influences it has not felt since its ejection eons ago. The approach happens gradually, over hundreds of thousands of years, as the rogue planet's trajectory gradually curves inward toward the gravitational embrace of its potential new stellar parent. The capture process that can transform a rogue planet into a bound member of a new stellar system requires extraordinarily precise conditions of approach velocity, trajectory angle, and stellar system architecture. The rogue planet must approach slowly enough to be captured by the star's gravitational field, yet fast enough to avoid falling directly into the star itself. It must encounter the stellar system at just the right angle to allow gravitational interactions with existing planets or debris disks to dissipate some of its kinetic energy and circularize its orbit into a stable configuration. The three-body dynamics that govern planetary capture involve complex interactions between the incoming rogue planet, the central star, and any existing planets in the system. These gravitational interactions can create resonance relationships that gradually modify the the rogue planet's orbit over thousands of orbital periods, slowly transforming a highly elliptical capture orbit into a more circular configuration that allows the adopted world to settle into long-term stability as a permanent member of its new stellar family. As your consciousness settles into harmony with these gentle capture processes, your breathing becoming as patient and measured as the orbital evolution that unfolds over cosmic timescales, you begin to understand how planetary adoption represents a form of cosmic second chance, where worlds that have experienced the trauma of ejection can find new homes and opportunities for renewed thermal and geological evolution under the warming influence of a different star. The observational evidence for planetary adoption comes from the discovery of planets in stellar systems with orbital characteristics that suggest they did not form in their current locations. These adopted worlds often have highly inclined orbits, unusual compositions, or orbital periods that don't fit the patterns expected for planets that formed within their current stellar systems. Statistical studies suggest that a small but significant fraction of planets in stellar systems may actually be adopted rogue worlds rather than native-born members of their stellar families. The thermal awakening that an adopted rogue planet experiences as it settles into its new stellar environment represents a profound transformation after millions of years of relying solely on internal heat sources. The warming radiation from its new parent star begins to heat the planet's surface and atmosphere, potentially melting surface ice deposits, reactivating atmospheric circulation patterns, and triggering geological processes that may have been dormant during the planet's interstellar journey. As you settle into the deepest layers of cosmic tranquility, you're breathing now as gentle and eternal as the gravitational fields that bind galaxies together across the vastness of space. Let your consciousness expand to embrace the profound peace that characterizes the existence of rogue planets throughout their endless journeys among the stars. These wandering worlds embody a form of cosmic serenity that transcends human understanding, traveling through space with the unhurried patience of entities that have learned to find completeness within themselves, carrying their own warmth, their own weather, and their own possibilities for life through the infinite wilderness of interstellar space. Picture yourself floating in perfect stillness in the space around a rogue planet that has been traveling through the galaxy for hundreds of millions of years, witnessing the profound equanimity with which this world continues its cosmic journey. The planet moves through space with such stately grace that its tremendous velocity becomes invisible, transforming motion into a form of cosmic meditation where change happens so gradually that each moment stretches toward eternity. This is existence at its most fundamental level. Matter and energy organized into a self-sustaining system that requires nothing from its environment except the freedom to continue its ancient journey. The philosophical lessons that rogue planets offer speak to themes of independence, resilience, and the profound beauty that can emerge from solitude when it is embraced rather than feared. These worlds demonstrate that isolation need not mean loneliness, that separation from original sources of warmth and light can lead to the discovery of internal resources and self-sufficiency that create new forms of wholeness and contentment. The cosmic perspective that emerges from contemplating rogue planets reveals a universe where home is not a place, but a state of being, where belonging comes not from external circumstances, but from the integrity of internal systems and relationships. These wandering worlds carry their homes with them wherever they go, creating portable sanctuaries that remain constant even as they journey through environments that span the full diversity of galactic space. The astrobiology implications of rogue planet existence suggest that life itself may be far more adaptable and resourceful than we have previously imagined, capable of thriving in environments that operate entirely according to internal energy sources and closed-loop environmental systems. If life exists on rogue planets, it would represent biological processes that have achieved the ultimate form of sustainability, complete independence from external energy sources, and the ability to maintain complex ecosystems for billions of years through careful management of internal resources. The scientific insights gained from studying rogue planets continue to expand our understanding of planetary formation, evolution, and the fundamental processes that govern the behavior of matter and energy in cosmic environments. These worlds serve as natural laboratories where planetary processes can be studied in isolation from stellar influences, revealing aspects of planetary science that would be impossible to investigate in traditional starbound systems. Rest now in the knowledge that countless rogue planets are peacefully traveling through space above your head, each one carrying its own complete world through the cosmic darkness, with a serene confidence of entities that have learned to find everything they need within themselves. These cosmic wanderers demonstrate that the universe provides endless opportunities for exploration, discovery, and peaceful coexistence with the vast scales of space and time that characterize our galactic environment. Let your breathing become as natural and effortless as the orbital mechanics that govern planetary motion, carrying with you the understanding that independence and solitude can be sources of strength rather than isolation when embraced with the patient wisdom that rogue planets embody. Sleep peacefully knowing that you exist within a galaxy filled with wandering worlds that demonstrate the possibility of finding completeness and contentment through self-sufficiency and the patient acceptance of whatever journey life may bring. Dream of planets drifting serenely through cosmic oceans of starlight, carrying their faithful moon companions on million-year journeys that connect distant corners of the galaxy through the gentle persistence of gravitational relationships that transcend any particular stellar environment. Rest in the infinite peace that flows through interstellar space, where time moves slowly enough for every breath to connect you to the eternal rhythms that govern the motion of worlds through the cosmic wilderness. The rogue planets continue their ancient journeys, patient and self-contained, carrying within their depths the warmth needed to sustain whatever forms of life and beauty may have developed in their protected environments. They remind us that peace can be found not in the absence of motion, but in the presence of purpose, not in the familiarity of surroundings, but in the integrity of internal systems that remain constant regardless of external circumstances. Sleep deeply in the embrace of cosmic tranquility, knowing that the universe provides countless examples of how to find contentment through patient travel, self-sufficiency, and the quiet confidence that comes from carrying everything you need within yourself as you journey through whatever vast spaces your path may traverse. The rogue planets drift on in infinite peace, and in their serenity, we find a reflection of the profound calm that awaits those who learn to travel through life with similar grace and self-contained completeness.